Hello, my name is Rita Rozental and I'm a mechanical engineering student at Johns Hopkins University. In this video, I will be dissecting a MS514 clockwork drumming toy. While modeled after older wind-up toys, this specific device was manufactured around 2021. It was purchased from Amazon for $13.99. The way that this works is that there is a torsional spring inside the toy, as you can see here. When the key is turned, the spring is wound tighter. When the key is removed, the energy is released and the spring unwinds and turns the gears inside the robot, causing it to move. This toy actually doesn't have any screws, and instead it has metal tabs that are bent to hold the outer casing together. There were also small metal rings which acted as fasteners. I used needle nose pliers to unbend the tabs and remove the fasteners. It's important to note that this toy is made primarily from tin, which is a pretty malleable material. The robot face and design that you can see here were likely printed on the casing during manufacturing. However, according to the manufacturer, the actual parts of the toy were assembled by hand. The outer casing and inner aluminum gearbox were likely punched and pressed into shape from a piece of sheet metal. This was done to enable more precise placing of the gears, their shafts, and fasteners. Now that the outer casing has been removed, the gears and torsional spring are visible. To further expose the gear mechanism, I again used needle nose pliers to open up the housing for the torsional spring. The first step here was to remove the outside aluminum plates surrounding the housing. The shafts and rods seen here are made of aluminum and were likely made using the extrusion method. These plates around the gearbox were also punched and pressed to make holes for the rods to fit through and move the robot arms. It is unlikely that laser cutting would have been used to manufacture any of these components, as it is too slow, wasteful, and expensive for mass production. Looking at the tarnished interior, it's important to note that a safety consideration in a metal device like this would be the prevention of rust. This is important, especially with all the sharp edges on this toy. In order to help counteract this, the manufacturer coated and painted the outside of the toy. As compared to the slightly rusted interior gears, the outside of the toy remains safe. As you can see here, the aluminum housing of the gearbox was much thicker and less malleable than the thin tin outer layer. This was likely done to protect the gear mechanism and prevent the gears from shifting with use. As the gearbox was opened, several of the gears came out and the torsional spring began to loosen, which can be seen here. After a lot of work with pliers and the key from the toy, the gearbox finally came loose, and the gears and torsional spring can be seen. This is an example of a compound ordinary gear train. All of the gears are spur gears, and there is more than one gear per axis. The big gear with the torsional spring around it is our driver. Here's a simplified diagram of the gears to hopefully help you conceptualize it better. So the driver gear is gear A, and it rotates counterclockwise because the key is turned clockwise, and as the torsional spring unwinds, the gear turns in the opposite direction. Gear A drives gear E and gear B prime, which is the smaller gear sharing the same axis as B. Gear B then drives gear C prime, and gear C drives gear D prime. Finally, gear D drives gear F, which moves the robot's arms. I counted the number of teeth on each gear in order to find the gear ratios. Basically, higher ratios mean that there's better torque, and lower ratios allow for higher top speeds. Calculated gear ratios make sense because the gears with the highest torque are the ones that are moving the robot's legs. Moving the arms requires higher speeds and less torque than moving the legs, so those gear ratios are smaller. Spur gears, failure typically occurs due to tooth bending stress, surface contact stress, or surface wear. The above diagram can be used to get an idea of where forces act in gears. Forces typically act along the pressure line, which is marked here in red. Coming back to our device, without the gearbox, it's much easier to see the torsional spring tightening. Here we see gear F driving a curved rod, which was also likely extruded and pressed into shape to give our robot a natural gait.